Okay. So this problem says find the magnitude and direction angle of the vector shown. If you have the notes at home, you'll notice, and I think we did this in second period, so my apologies for the time not realizing this. But if you look at the coordinate plane that I provided and the vector that's over here, if you graphed this vector according to the run and the rise, it'd be up over here somewhere, which is kind of wonky. So I think to make the problem fit the coordinate plane, we should make this -7. So again, my apologies to second period for not catching that sooner. But to find the magnitude, and remember magnitude is just a fancy word for length, to find the length of this vector and the direction, obviously we want to draw a picture for it. When you're given the component form of this vector, keep in mind that this is the run and this is the rise, right? The whole, we call the technical term is horizontal component and vertical component, okay? But they're the run and the rise if you relate it to what you talked about back in Algebra 1. And in order to graph this, we start at the origin and we move this far to the left and that far down. So if we go 3 and 5, and then come down 3, 5, 7, okay, down to here, we connect, this is our terminal point, we connect this to there. I can do better than that. I got a smart board, right? Might as well use it. So we connect like so. So here's our vector, okay? Now, as far as the magnitude is concerned, keep in mind, this distance here, our rise is -7, and our run, this distance here, is -5. So to find the magnitude, which is essentially the length, this is, it's a Pythagorean theorem formula if you want. You could call it the distance formula from 0, 0 to -5, -7. All right? The magnitude formula that we've already talked about in class looks like this, okay, where V1 represents the first component here and V2 represents the second component. So if we want to find the magnitude of vector V, we take the square root of -5 squared plus -7 squared. Make sure you're putting parentheses around this again for the 100th time, because when you square this, you're going to get a positive number, right? If you try to do this in the calculator without these parentheses, you're probably going to get a negative number. Okay, so from here we take the square root of 25 plus 49, which is the square root of 74. Okay. I guess I'll pull up Desmos here, since we're working from home. And I don't know what the situation in your calculator is right now. We'll work from Desmos. Okay, if you're going to work with Desmos, make sure that you are in degree mode. So click the wrench, come down here to degrees. Okay, that's going to make a difference. What did we have here? We had the square root of 74. So we get 8.6. 8.6 here for the magnitude. That doesn't have any units right now. It will once we start doing some of these applications. Okay. Now, as far as the direction is concerned, remember, when we're doing vectors, the direction angle of a vector is always measured from the positive x-axis. That's in any sort of problem that doesn't have a context to it whatsoever. So we're measuring this in what we used to call standard position back when we first started talking about the unit circle. Standard position measures from the positive x-axis counterclockwise. So the direction of this vector goes from here all the way over like this. All right? But given what we know about this picture, okay, and we've already discussed how this is a right triangle, what we're going to find is we're just going to find this piece of the angle. And then we're going to have to do a little bit of piecing together problem solving to get the entire angle. So if we're looking for this angle, and we've been calling this angle theta, and we know this side is -7, and we know this side is -5. And again, -7, forget the fact that distance can't be negative. We're just labeling it -7 because of this. If I want to find this angle, and I have this right triangle with these two sides, this side over here is the opposite side, this side here is the adjacent side, so we have those two sides to complete this trigonometric ratio. So that would be our tangent formula. And that's a formula that we've already discussed. If you want to know theta, take the inverse tangent of the opposite side over the adjacent side. Now if I go back to my calculator for this and plug this in, okay, under the functions button, you have trig, here's inverse tangent, the inverse tangent of -7 over -5. We'll round this to the tens place as well, 54.5 degrees, right? I mean, that's what the formula is telling. Taking the inverse tangent of -7 over -5, 55.5 degrees. So if we jump back to here, if you just blindly trust whatever number comes out of this formula and you say, yep, that's the direction angle. We said just 2 minutes ago that the direction angle of this vector goes from here, from the positive x-axis, all the way over to here. So a decent picture will tell you, with this number you got from the formula, that the angle that you just calculated is this angle right here. That's clearly not this angle, right? It's just this piece. So that's why we need to have a picture when we're working with vectors like this, okay? Because you can see from here that this is our 54.5 degree angle, which is tacked onto, for lack of a better word, tacked onto the first piece, which is moving from here all the way over to here. That's 180 degrees. So we have 180 degrees just to get to this point, then we have another 54.5. So to get the correct direction angle of this vector, we have to add 180 to this number to end up with 234.5 degrees. Okay, so this answer that I put a box around the first time, technically that's not correct. We need that in order to come up with the direction angle, okay? But this is the correct direction angle for this vector.